Good morning to all. I am G.Lingasamy, Associate Professor in EC Department, P.S.R Engineering College, Sivakasi. Now the topic is unit junction transistor. We know that the special type of semiconductor device here, the unit junction transistor has 3 terminals and 1 p-n junction. Due to the single p-n junction, it is called unit junction transistor. This is the unit junction transistor. Here, base 1 and base 2 are the base terminals, and emitter is the emitter terminals. Totally 3 terminals and 1 p-n junction. Generally, the UJT is a lightly topped N-type semiconductor bar in which the heavily topped P-type materials are alloyed in the N-type bar. The P-type materials is located nearby terminal B2. Therefore, the total resistance due to the bar is divided into 2 parts. One part is above the P-type layer and another one is below the P-type layer. This is a symbol for UJT. Here, the emitter terminal is slanted for some angles. Again, B2 and B1 are the terminals. The equivalent circuit for the UJT is here. Therefore, the bar consisting of RBB, the total resistance due to the bar is RBB. The RBB is again divided into 2, RB1 and RB2. Here, the above the point A is R2 or RB2, and below the point A is RB1, simply R1. Here, the PN diode is at the point, the cathode is at the point A. Therefore, it is the equivalent circuit for UJT. For operation, generally the RB1 and the RB2 both constitute the total resistance due to the N-type bar. Therefore, whenever we apply the VBB for some voltage, therefore the potential is gradient takes place in the silicon bar. Therefore, at the point A, the voltage is VA, V suffix A, that is a voltage at the point, that is a cathode. And this is a B1, at the B1 is 0, and the VBB is B2, at the point B2, the VBB. Whenever the emitter voltage is 0, the VA has some value according to the VBB. Therefore, the current flow through the bar is VBB divided by RB1 plus RB2. Therefore, the voltage at the point A is VBB divided by RB1 plus RB2 into RB1, because the potential at A is the current flow through the RB1 into RB1. Therefore, here VA, the voltage at the point A is equal to VBB into RB1 divided by RB1 plus RB2. Now, at the point A, the potential is created according to the application of the VBB. And VE is 0, not connected. The potential in the emitter terminal is not connected. In that condition, the PN diode has the reverse bias, because cathode having some voltage and anode having 0 voltage. Therefore, it is acting like the reverse bias. Due to the reverse bias, the current, there is no current in forward direction. Only the leakage current flow through the device due to the minority carriers of the PN junction. Therefore, the current, the light current, that is a leakage current flow through the RB2 to emitter. This is very much less amount of current. Now, we apply some voltage, emitter voltage in this direction, just increasing the voltage. Therefore, whenever emitter terminal is equal to the voltage at point A, Therefore, it is neutral. That is, both currents, both voltage are equal. After that, therefore, the current flow through the device is 0. After that, whenever the emitter voltage is increased beyond the threshold voltage above the VA, that means whenever the VE, which is greater than VA plus VT, here VT is that is the threshold voltage of the diode. In the case of silicon, this is 0.7 voltage. In case of germanium, it is 0.3 voltage. Therefore, VE is greater than, whenever the VE is greater than VA plus VT, the diode turn into the conduction operation. Therefore, the diode turn on. The current flow through the device is increased beyond that voltage, VA plus VT. In that point, the holes in the forward bias of the diode, the holes are emitted into, that is, holes are jumped into the silicon bar at the point A. Due to the potential gradient of between B2 and B1, the potential in the point B2, the terminal B2 repels the holes in downward direction, while the P2 attract the holes in the downward directions. Therefore, the holes are accumulated. Due to the accumulation of the holes, the resistance between VA, the point A and B1 is suddenly decreased. This is called a negative resistance. Therefore, whenever the resistance is decreased, the current also increased by increasing the voltage. This is up to certain level, that is the peak point level. Therefore, up to the voltage attained at Vp, up to Vp, the current is maximum. That is not current is maximum, voltage is maximum. After that, beyond Vp, the voltage is reduced and the current is increased to a certain level. That is a value point. Up to the value point, the voltage is reduced to value voltage and the current is increased. Beyond the value point, it acts like ordinary PN diode. Therefore, after the value point, the diode conducts just like the PN diode. This is a VA characteristics of UJT. In general, in X axis, the voltage is taken and in Y axis, the current is referred. But in this case, in X axis, the current is represented and in Y axis, voltage is represented. Now, at that point here, this is the reverse current. Whenever the voltage is 0, here is the voltage representation. This is the current representation. Whenever the voltage is 0, therefore the diode, that is the PN diode, acting as the reverse bias condition. Therefore, only the leakage current, the minute leakage current is flowing through the device, that is this much. This is a negative charge, negative current. That is the current passes in reverse direction whenever the VE is 0. After increasing certain value up to this level, the current is gradually decreased and at the point whenever the VE, which is equal to VA, the current is 0. After that, beyond the VA, it is increased up to the peak level. The peak level is nothing but Vp, which is equal to Va plus Vt. That is, this is due to the threshold voltage, the increment of the threshold voltage. Already told the threshold voltage for silicon diode is 0.7 voltage and germanium is 0.3 voltage. Therefore, Va plus 0.7 voltage for silicon, it is Vp. At that point, Vp, after increasing the voltage, emitter voltage, the voltage falling down towards the value point. Therefore, the current is also increased towards the IV. The IV is increased 1, the voltage is dropped down to the value point. At that point, after the value point, the diode acting like the forward bias and ordinary PN diode. Therefore, the UJT act like the ordinary PN diode. This is the operation of the UJT. Now, this is the cutoff region beyond this level. That is a negative shift. This is a cutoff region up to the peak point. After that, the gradual reduce in the voltage and the increment in the current is called a negative resistance region, because the resistance is gradually decreased and the increment of the current. After that, this is the saturation region. After the point IV, the diode act like the saturation. Therefore, there are three parts in its operation. One is cutoff, and another one is negative resistance, and another thing is saturation. These are all the operation of the UJT. Here, the calculations from this UJT, RBB is nothing but the addition of the RB1 and RB2, because the entire silicon, the resistance due to the entire bar is RBB. Therefore, the RBB, total RBB is divided into two, the above the point A and below the point A. Therefore, above the point A is RB2 and below the point A is RB1. Therefore, an addition of RB1 plus RB2, which is equal to RBB. Therefore, the VA, the voltage at the point A, which is equal to eta VBB. Therefore, eta is nothing but RB1 divided by RB1 plus RB2. That is, eta is called intrinsic shunt-off ratio. Intrinsic shunt-off ratio. This is normally the intrinsic shunt-off ratio is from 0.56 to 0.75. Accurate value for the that is a range of the intrinsic shunt-off ratio is from 0.56 to 0.75. Here, therefore, the peak voltage, which is equal to, this is eta VBB plus that is a threshold voltage of the diode, that is VT. In other words, this is the what is eta is equal to, in other words, Vp minus Vt divided by VBB. To find the intrinsic shunt-off value ratio for any device, we can calculate from the equation Vp, that is a peak voltage, minus the threshold voltage, that is a 0.7 for silicon diode and 0.3 for germanium diode. According to our applications, it is the Vt is 0.7 or 0.3. Therefore, Vp minus Vt divided by VBB is the intrinsic shunt-off ratio. We can find the parameters, we can find the characteristics of the UJT by using this intrinsic shunt-off ratio. And yes, now this is the negative resistance regions available in the UJT operation. It is used for relaxation oscillator and a pulse generator. Some applications are the trigger controller and so on. These are all the applications of UJT. Okay, thank you.